As we all know, designing electronic circuits can be extremely complex and mathematical. The aim of this presentation is to introduce the concepts of computer-aided design using software. Much of this presentation has been put together using LTspice. There's a few things in from other places that I've found information. And I have to say that I am nothing whatsoever to do with LTspice or analog devices. Everything in this presentation is from my own experience and my own research, and is given in good faith. So, no comebacks on that one. So the background to simulation. Designing electronic circuits, as we said, is an involved process. In the early days before computers, everything was done longhand, all calculations done on paper and early calculating machines, and everything drawn out by hand, and everything calculated using trial and error, birds nesting circuits together and checking things that worked, and a lot of manual labour. Then slide rules came in, and calculators. Mr. Sinclair and one or two others brought some nice calculators together in the 70s, which helped. However, with the advent of integrated circuits, which have got thousands of transistors and hundreds of other devices on them, designing became a whole new level. So SPICE was created at the University of California, Berkeley in the USA, as a class project in 1969 and 1970. So it's not new, it goes back 50 years-ish. SPICE stands for Simulation Program with Integrated Circuit Emphasis. So from day one, it was aimed at designing integrated circuits, which was the new thing in the late 60s, early 70s. And over the years, it's evolved to become a worldwide integrated circuit simulator, but it's much more versatile than just ICs. So SPICE was the first computer program for simulating performance of integrated circuits that was readily available to undergraduate students for the study of integrated circuit design. It's been used to train many students in the intricacies of circuit simulation. I just put my teeth back in. However, SPICE was much more than a simple program for instructional use. It was the first to incorporate sparse matrix analysis to permit economic simulation. What that means, if you can cast your mind back to your A-level or degree maths, matrices, whole arrays of numbers, and the sparse matrix is where lots of the elements of the matrix are actually zero, and it's easier to calculate. There's less calculations. They used something which is called adjoint analysis for sensitivity to component variations for things like Monte Carlo analysis and what have you, so you can run various scenarios. Adjoint analysis is basically an inverse matrix. So if you had a 4x4 matrix, sorry, 2x2 matrix, A, B, C, D, the A and D get interchanged and the signs of the others two get negated, and that is an inverse matrix. Don't ask me for the maths because I cannot remember that far back, but that's the basis of it. It was the first to have built-in device models, so you could get a first cut design fairly close. And it has a relatively simple user interface that's evolved through starting off with punch cards, if you can remember those, to dumb terminals, and then on to sophisticated workstations. I've put a reference in there, so if anyone wants to read up on sparse matrices, there's a link for it which leads you to where I got this from. So SPICE and its descendants have become essential tools by virtually all integrated circuit designers and other analog and digital circuit designers too, for that matter. It's not limited to just integrated circuit design. It's a very versatile program. So SPICE can be used to simulate circuits of almost any complexity. There's been a number of descendants appearing over the years under different names, and they don't all necessarily contain the word spice. Electronics Workbench was going around in the 90s, 80s, 90s. That now has morphed into multi-sim, which because National Instruments bought Workbench. There's a program by Texas Instruments called TINA, which is also spice-based. And then LTspice, excuse me, was originally by Linear Technology, which is now part of Analog. And that's just a few of the programs. There's dozens and dozens of them. Many of these programs, they cost hundreds or thousands of dollars to either buy or to license on an annual basis. Software licensing is a very lucrative thing, so a lot of them will just license it. You pay your yearly fee and you get the use of it. This includes PCB CAD packages like Altium Designer and many of the other PCB CADs. They've got a Spice addition to them. Some of them don't come with it. You have to buy it as an add-on, so it costs you more money. By contrast, LTspice is free. Yes, free. You just download it. Texas Instruments TINA is also free, but it's a limited node version, so you can only do small circuits on it. If you want the full works, then you have to pay for it. LTspice is completely unlimited. You can, in theory, do something with 1 million transistors in it if you wanted. There is no limit. So the man behind this is a guy called Mike Engelhardt, and there's a cartoon likeness of him in the background there. He took the original Barclay Spice software and virtually rewrote it, making it much more accurate and crucially much faster, which is where that matrix manipulation stuff came in. Linear Technology was originally a company that grew up primarily manufacturing power supply regulator ICs, and they were one of the first companies to make switch mode buck regulators and step down top that side, but switch mode power supplies. So originally this program was actually called Switcher CAD, and as their primary objective was to use it to simulate switch mode power supply ICs. It was later renamed LTspice. There's the man himself, Mike Engelhardt. This was at Reading in 2024. Unfortunately, because this is not full screen, you probably can't see that, but I'm in that picture. I'm there. You can just see my bald patch. And the guy sat beside me is the late Paul G. 8 XBE, worked at Wood and Douglas with me at the time. So this was at the one of the hotels in Reading. So he does world tours and does the business, telling people how to use LTspice. And there's nothing like having the author of the program in front of you, because if he doesn't know, no one will. Yeah. So why simulate? What does it do for us? It allows us to develop electronic circuits without initially buying any components, not having to wield a soldering iron, no need to buy or make a circuit board, no requirement for expensive test equipment. You'll likely need all of those later, but simulation will give you a head start. You're less likely to damage components later on because your design is going to be close-ish to what you want. It's also quicker, and more importantly, you don't burn your fingers. Or get a shock. So how does it work? It relies heavily on models. Every component has a set of characteristics. So for a resistor, for example, if you put a voltage across the resistor, you get a current through it. If you double the voltage, the current doubles. So you've got a transfer curve. For a resistor, it's a straight line. For other components, it's different. And for multiple components like integrated circuits, flip-flops, or op amps that are multi-pinned, then obviously you then get a matrix of characteristics when you look from pin to pin. So all of those are nowadays modelled and measured and confirmed by the manufacturers, and there are literally millions of SPICE models available. You have to be a little bit careful though, because different SPICE programs have a slightly different format for their models, which sounds a little Irish, but you have to make sure that when if you import a third party's models, that they are either aimed at LTspice, or if they're general SPICE models, you have to make sure that all the parameters are in the order that SPICE wants them. I mean, that actually importing third-party models is another talk on its own. But many models, many component models are already contained in the LTspice program as you download it, and most manufacturers will provide models too. You can just go to their websites and look for component model libraries and download the one that says LTspice, and then you can use them. So intrinsic to SPICE is the ability to model basic and more advanced single element real and ideal components. The SPICE models have a number of specific parameters that control how the simulation model will behave under varying circumstances. For example, you can change temperature coefficients for a resistor and run a temperature simulation. So you can change those coefficients to closely manufacture a vendor's component if you haven't got the model for it from their website. Or if it's there, you can download the exact model. So in order to do any measurements, once we've actually generated a circuit, we need, first of all, a source of some signals. So we need a stimulus. So we need pulsed voltages or exponential voltages, sine waves, DC supplies, and sometimes arbitrary waveforms that you can define. All of the above can be programmed to simulate real-world test equipment, just about. It's a little bit quirky, but you can do it. So then you need something to measure the outputs of your circuits. So again, there's virtual instruments, and they almost all are based on this graphical output. This is called a plot plane in LTspice, and this one I've actually got 4 plot planes, one above the other. It's easier to do it that way because if you've got several traces that are all very similar, say you've built an amplifier and you've got a sine wave going in, when you plot them all on a single pane, sometimes they overwrite each other and it's very difficult to see which one's which, although they are color coded. It's not the best display, has to be said. But there's means of displaying frequency, amplitude, DC voltage, phase angle, and they all come up in this sort of graphical plot arrangement. So how does it work? Libraries. We have loads of libraries, so they store the data for the components. So every SPICE component has 2 main parts. It has the schematic symbol, some resistors there, op amp, voltage source, etc. And then if we right click on the component, we can actually find a component value in a list, or we can edit it ourselves, depending how we're going about this particular simulation. We can also add those extra bits and pieces that I was talking about. So here we've got a transistor that we can add various bits and pieces. That's the capacitor. We can add, in the capacitor we can add the loss component, because not an ideal capacitor has no losses, whereas an electrolytic capacitor has some resistive losses. Some of the ceramic capacitors will have a phase components, particularly RF capacitors will have a dielectric loss, which you can put in and simulate more of a real world component. With the transistor, when you pull a transistor off the component library, you just get either a PNP or an NPN, and then you can select from a range of devices that you've got library parts for. You can have a power transistor or a small signal transistor just by picking one. It says there, pick a new device, so you can pull up a list.
So that when you say pick a device, that's readily available devices now? Yes.
Ones that are in the library.
Yeah, well, the way I was thinking of it, you could do the circuit simulation using germanium, work it all out, and then change some of the transistors to silicon and see if it affects the circuit.
I can't remember if there's germaniums in the library, but if you wanted to, you could pick a device, go in and edit the SPICE commands for it. So instead of VBE being 0.7, you could change it to 0.3. You can actually do that. It's reasonably straightforward, but there are pitfalls doing it.
No, I understand obviously the reason for doing that. So I'll ask a question.
Okay, so LTspice comes with a host of example circuits, and they're all in two libraries. For whatever reason, they've decided to call them jigs and educational. Well, educational, that's pretty straightforward. Those are circuits that are there for you to play with. They don't necessarily work, but they are schematics that you can see how things have been put together, etc. Now, the jigs are all working circuits, and you'll find if you bought devices from LT back in the day, their data sheets normally give an example circuit, as most data sheets do for devices, a working circuit. And the jigs will be those working circuits. So if you build it with the components specified, it should work. So one of the peculiarities of LTspice is when you install it, it doesn't put it in its own directory. So a lot of it ends up in program files, Windows program files, which is a bit of a nuisance, but so you have to go looking for stuff. We'll come on to that in a bit. So where do we get it? You go to, if you put in your browser LTspice download and click go, it should come up with this page, which is the analog devices. And then there are various choices. I'm sorry, this is a bit blurred because it's not full screen. You've got various versions of Windows or Apple or whatever. So you select the right one for your particular platform, Windows 10. I think they've still got back to Windows XP if you really want it, if you're still running a Windows XP machine.
Does it have a Linux version or not?
Sorry?
Do they have it for Linux?
I think so. Yeah. Unfortunately, I can't read that. It's gone blurred, so this is not quite working out as I'd hoped. So anyway, download the correct version for your platform, and then obviously click the executable and install it in the normal way. And eventually the install will appear in the folder program files in a folder called LTC, and then in a subfolder to that, LTspice 17. You should just about be able to read that there. So this is a typically installed folder. So this is LTspice 17 in the LTC folder. So you've got examples, which has got the jigs and the educational in, and then you've got libraries, which is all of the schematic symbol libraries and the component libraries. They're all in there. And then there's various other things that develop in this folder after you've used it a few times. Okay, that's the opening screen once you've got it installed. So typical Windows screen. Main commands at the top. Obviously, the first one is the file commands, which allows you to open the file. We'll look at this in a bit more detail in a second. And then you've got your standard toolbar, which has got things that buttons to allow you to do the various functions. Until you put a schematic in, most of them are grayed out, as you would expect. So homing in on those, if we look at the file, you've got new schematic, which obviously if you're drawing from scratch, you click that and it gives you a blank drawing canvas. New symbol, let's say that you want to draw an IC that's not in the library and you can't get it from anywhere else. You've got a peculiar IC from the past. You can draw an outline for it and then develop the parameters for it if you're that advanced. That's not easy, but the facility is there. So, and then down here, you've got a list of the last files that you had open. So you can just click on one of those and it will take you straight back to your design. If it isn't there, then obviously you've got to go file and drill down the directory structure for it. The next one, view, just allows you to turn on and off the various toolbars or the status bar, etc. Don't normally worry about that one, they're normally all ticked. And then the third one along, tools, you've got control panel and you've got color palette and you've got a sync button which allows you to resync the installation you've got with what's on their server because they're continually updating this. So in the tools menu, you've got control panel, and my advice is unless you really know what you're changing, don't change anything in there. The only time I've ever come across having to make a change in there was the last time when I was at EDMI, my last job. One of the engineers we had in Norway did a simulation of a high kV pulse generator that we had to actually use to test surging on meters. And he had to, because he wanted such a rise time in such a quick amount of time, nanosecond rise times, he had to change one of the parameters in there in order to get the calculation time right, because otherwise it didn't work. But that's the only time I've ever had to go in there and change something. Not so much this one. This one allows you to change the color palette. So on your output graphical display, standard it comes with a black background. I've changed it to gray in this one just to show that it can be done. But again, you've got to choose your colors carefully because otherwise the clarity of it isn't good. That's probably the most used one, the help screen. You could either click the help screen and get the drop-down menu, or if you just want help topics, the usual F1 function key will bring it up. And the other one is it just tells you about, if you click about, it will tell you which version you've got and some copyright dates. It's not particularly useful, but it's a standard thing on Windows. The help screen, as I say, is probably the most used one. So you've then got 4 tabs on the top here. The first one is a list of subjects, and each of these you can click on the little square and either expand or contract them. Those have been expanded. The ones down here have not. Otherwise, it would be way off the bottom of the screen. So that's fairly interactive. You then have an index of what's on there. So you can either scroll down or you can put something in the search box at the top, hit return, and it will have a look. The only thing I found with this is some of the terminology is a bit American. So It's a bit like we call the bonnet on a car and they call it the hood, and you know, there's a few things like that that you don't always get what you expect to come back
Can you
up.
edit those?
Sorry?
Can you edit those?
No.
Just don't put a U in anything. I remember how I spell aluminum.
You can do a complete, you know, a search on just about anything. I mean, in this particular instance, you probably can't read that, but I put BJT in the search for bipolar junction transistor, and it's come up with some entries. And if you then double click on those, it will put that information in that pane there, so you can actually read what you've searched for. And then the last one, if there's subjects you go to a lot, you can actually put them in your favorites box. So you can add a favorite once you've looked it up, which again, I've never used. So if you haven't used it for a while, it comes up and reminds you, you haven't used this for 139 days or however many days it might be. Do you want to update? And it gives you the choice, yes or no. If you say yes, it will look at your installation on your machine. It will look at the files you've got, the libraries you've got, and then it will do a comparison with what's on the server. And it will then download all the bits you haven't got, and it will update for you. Free of charge, no reason why not to do it. Okay, let's have a bit of a demo then. So what I'm hoping to achieve, I could have done without the screen issues, but I'm going to do a basic schematic edit, and we'll run a simulation and then explain the various simulations, what's the difference between a transient analysis and an AC analysis, and stepping component values, voltage values, etc. And I mentioned arbitrary waveforms. We could do what's called a PWL file, where you can actually put in values to, say, simulate a video waveform, for example, which you obviously can't easily generate with any of the other sources. So okay, there's the screen. That's the start current screen. So let's have a quick look. There's the drop-down menu. So new schematic, new symbol, open the file, set your printer up, and then there's the list of files. View, said toolbar, status bar, window tabs, tools, control panel. We'll have a quick look at the control panel. So you've got all of these various parameters, various menus behind there. But as I say, unless you absolutely know what you're changing, it's best left as the original default values. This is one of the values I had to change. I seem to remember, and it was one of these in this list, and I can't remember which one. That's a little while ago. But if you change it when you close the program down, it doesn't remember it. So you have to change it again. So at least if you mess it all up, you can close the program and open it again.
Well, there's a refer to defaults there as well. So
yes,
seems
yeah.
strange that it doesn't remember it.
I think it remembers it for the session, but if you mess it up, you click defaults and it will go back.
Yeah, it'd be a bit annoying if you change 3 things each time, wouldn't it? That you've got to redo that every time you launch it.
Well, you probably only want it. You only want it for that particular circuit that you've done. And if
can you after you've changed it and so on, can you then decide, yes, this is a version I want to keep, therefore I can save that as a separate project, a separate plan?
unfortunately not. Well, not that I know how to do anyway, let's put it that
Might
way.
be a way of saving the conflict, mightn't there? somewhere?
Yeah.
So, there we go, there's another way to get into the help. So let's have a look. There's the index. If we just go on to measure, there's all of these different commands. The thing with this program is, with any Spice program, is you don't necessarily have to use the toolbar. Once you get to know the structure of the commands, all Spice commands begin with a dot. It's a bit like programming in a programming language. You can either have an executable command or you can have a comment. So anything with a dot in front of it is a command that will happen with the simulation. If you wanted to put in, this is the supply voltage, then you'd put a semicolon in front of it and that becomes a comment. So that's the help file. Search, if we put, let's go JFET. So that's come up with JFET, junction FET. Double click on it and it will tell you all about JFETs, what all of the parameters are. So if you're editing one of the parameter files in the component library, you know what all the symbols and the names are. As you can see, JFETs have got quite a large number of defining parameters. And of course, if you get any of them wrong, your model's not going to work. I mean, these are some of the things that you will obviously vary between transistors. I mean, the threshold voltage is the voltage which the FET turns on at, and it varies between small signal FETs, which will have a relatively low voltage, but if it's a power FET, that might be 5 or 6 or 10 volts before it turns on. So you'll find all those parameters are different between devices. And as I say, favorites, I've just looked JFET, I could add that in, and that's now my favorite. So I don't have to go through the search. I can go favorites. Oh yeah, JFETs, click it. Okay. New schematic. When you click new schematic, that strange background disappears and you end up with a blank canvas. And then you see a lot of the symbols on the toolbar have now filled in. They're no longer grayed out. So what have we got? The running man is literally run the simulation. The hand, halt, stop it. Zoom in, pan, zoom back, zoom to full screen. Then you've got tile windows. If you right click on that, you've got a whole load of things you can do there. You can tile, when you've done the simulation and you get the plot plane up, normally they come up one above the other, but if you want to, you can tile them side by side. And if you've got several plot planes with about 5 or 6 graphs on, if you have the horizontal tiling, all the graphs are long and thin, so it's not so easy to read them. And then you can close everything. And again, you've got the file commands, new schematic, etc. in there. You can cascade the windows. You can close all. The scissors is a cut. If you've got schematic, and we'll do this in a minute, and you want to remove a component, you just click the scissors and then click on the component and it disconnects it. If you've done the circuit, say you've done I don't know, a small amplifier or something, say you're doing an audio mixer and you want several channels, if you've done one, you can then copy the whole block and paste it, so you can actually quickly replicate blocks of circuitry. Or even if you just want to, if you've forgotten to put a component in, you've already got it on the board, you can just copy another one. The binoculars is just search if you want to find something. If you've got a big schematic and you can't spot it, you can search for it. Print setup, print command. This is the wiring tool. So once you put all your circuits together, all your components on, you can then join them up. Brand symbol. Net labels. One of the things you can do, you don't have to wire everything together. Sometimes the wiring gets just like a rat's nest on a CAD program for laying out printed circuit boards. You get things overlaying each other. So if you had a power supply, for example, you could put power supplies up the corner and then put a label on that says plus 5 volts, minus 12 volts. And then wherever you want that to connect to your circuit, you can put an identical label, and then those two are connected without actually joining them with a line. So that's quite useful. Old-fashioned resistor, squiggle instead of the modern rectangular. Capacitor, obviously, inductor. I don't know why they've done this. You could go straight to diodes, but they're the only active components that you can actually access directly. Everything else is behind this gate symbol, which leads you to component libraries. And then you've got two hands there, which are move commands. If you use the larger of the two hands, that allows you to move a single component, but it doesn't take anything with it. Whereas the smaller hand is a drag symbol. So if you drag a resistor, for example, it's got connections to it, the connections will go with it. Useful at times. And then you've got undo and redo. Then rotate. You can either rotate the component by keyboard structure functions or symbol up there. A menu. And then you've got a text editor for making comments. And the one at the end is if you want to make a SPICE directive. So most of what you need is already up there. So let's put some components up. Now if I press Control and R, I can rotate the component. And you'll see why I'm putting that resistor there in a minute. Put capacitor down there. So let's go and find a transistor. Let's have, where are we? That's quite difficult to read, isn't it? There we are, NPN. Let's have an NPN. So we click OK, and that gives us our NPN. Don't want two of them, so right click to get rid of it. A little bit out of focus. Yeah. Okay. Thanks, Bob. So now I want to just rearrange these very slightly. So I want to move that resistor. So I just pick the symbol. Like so. I forgot that I want a capacitor, another capacitor. So let me do copy. Oh, sorry. Copy. And left click to place it. I want to move that one down here, and I want to rotate it, so it's Control R. That's going to be my input capacitor. Let's wire a few things together. Oh, let's before we wire things together, let's have a ground symbol. If you want to scroll something, it's just the scroll button on the mouse, and if you scroll from above, it expands it below. If you scroll from the right, it expands to the left. If you scroll from the left, it expands to the right. So you've got a reasonable amount of control where you can position it, or you can just hold down the left mouse key and you can just move it around. Okay, so let's do some wiring. Now, the one thing about this program, unlike a lot of programs, I can go straight through the components, like so, and it doesn't short them out. This one's really in the wrong place. It wants to be up there. That wants to be there. So we'll carry on wiring. Okay, and right click to release it. If you don't right click and you take the cursor off the screen, it scrolls down because it's expecting you to wire something further up. So I must admit I do this all the time by mistake. It's annoying. I forget to release the wiring function. So that one's now in the wrong place. That needs to be there. So for the moment, I'm going to wire that through there and into there, and that into there. Again, you'll see why in a minute. Now, LTspice and most Spice programs, all Spice programs, they refer everything to ground. So even if you've got something with a transformer or an opto-isolator in it, and you want the input and output to be isolated, you have to have a ground on either side. As long as you connect it to your circuit with 100 mega ohm resistor, it will work. If you don't, Spice hates things floating. So if you can't have things floating, it does funny things to the matrix. So as long as you've got something that ties it, even if 100 mega ohm resistor is to all intents and purposes open circuit, but it allows the program to function. Okay, so we've got basically a common emitter amplifier there. Got no component values on it, and we're going to need two things in order to simulate this. We're going to need a source and we're going to need a power supply. So if I go into components and we scroll across, and this is the other anomaly as well. In the component libraries, you've also got the test equipment. So and it's not apparent where they are. So I click on a voltage and I get a voltage. And I'm going to need two of those because I'm going to need one for supply and I'm going to need one for a signal source. So again, I need grounds. And again, I'm going to wire things in so that I can go on there, straight through on that one. Now on this one, I'm going to just wire straight through, and I'm not going to connect those two. I'm going to put a net label on here, and I'm going to put on my net label plus 6 volts. Okay, and that gives me a net label, so I'm going to stick one on there. I'm going to stick one on there. Those two are now, as far as Spice is concerned, connected together. if I right click on that, I can now put a value in. Let's have 6 volts. So that's now telling me that's a DC supply. The negative is ground, so it's a positive 6, which is what I've put on my label. This one I want to be an AC supply, an AC source. So to do that, I have to go into advanced, and then I have a range of functions that I can check to set it up. So this time I want a sine wave, so I collect sine wave. I can have a DC offset, so instead of the center of the sine wave crossing through 0, you could set it up on a volt, 2 volts, whatever supply you want. You can set the amplitude. Let's set that amplitude to 50 millivolts. You don't have to put the whole millivolts in, but you have to put M in, a small m. If you put a large M, it's accepted as mega. You have to put meg, M-E-G, with a large M to distinguish. So we'll come to that in a minute. Frequency, what do you want? Let's say you can either, let's say we want a kilohertz, so you can either put 1000 in without any terminator. It doesn't have to have hertz after the end, or you can go 1K. It will recognize that. We don't need anything else. If this was going to be a pulse waveform, then we would put rise time, fall times, stuff like that, but you get a slightly different menu. You could add a phase delay. It's a sine wave. You could have it, instead of starting at 0, you could have it starting at 90 degrees or any other phase angle you want at the point of starting the waveform. And for some strange reason, you've got this AC amplitude. Although you've put amplitude here, it needs an entry in there, basically a 1. Otherwise, it doesn't always generate a signal. So
Is your phase delay on there? Does the circuit, when the circuit's analysed, does it just seem that the circuit is at 0 phase?
if you tell it unless you tell it otherwise, yeah.
And then when you actually set the phase on your input signal, that's relative to 0 for the whole circuit?
No, it's basically if I was to put a probe on here and graph the output from that signal generator, from the moment of starting, it will start at 0. Circuit steering.
Right.
Live streaming is on.
It'd be whatever the circuit decides.
Well, yes, of course. I mean, if you've got a filter or an RC network, then you'll get a lagging phase shift. But all that really is just to tell the source generator where to start initially. Okay, so if I click OK, that's now given me to move that. So let's call that AC1, let's put that down there. So that's now telling me I've got an AC supply and I've now got the sine wave with 0 phase shift and 50 millivolts, and this is RMS. This is not peak. This is just half the waveform effectively, and my frequency is 1 kilohertz. Okay, right. I can't do anything yet because I've got no values. So where do we start? Oops. Let's have a, I don't know, let's have a 1K, let's have a 1K load. So we've got 1K load resistor. What should we have? I'll put 10K upper bias resistor. Let's do a 1.5K, 1K5 lower resistor, and let's make that 1 ohm. And this is the other peculiar thing with Spice, is you cannot have zero. It doesn't like a resistor being zero because you get divide by zero errors in the maths. You can have 0.00000001 and it will accept it, which is again odd, but it's the solving of the matrices. So I need that one. I need that resistor in a little while just to be able to change the simulation. So let's make that one 100 ohms. And because it's ohmed, it doesn't need a terminator. So 100, it will recognize 100 as 100 ohms. Capacitor, I'm not going to bother with voltage rating. It doesn't, we're just using effectively ideal components here. So don't need equivalent series resistor. I just need a capacitance value. I'm going to put 100 microfarads in there. So 100 and a small u. That'll give me 100 microfarads. So one more to choose, which is the input capacitor. I'm going to make that, let's make that 1,000 puff. Small p for 1,000 puff. I should have something that might work. It may not. So if I now do a run, I've got 1,000 hertz, so that's one cycle for every millisecond. So if I do a stop time of say 20 milliseconds, that should give me 20 cycles of waveform. I'm not going to fill anything else in. I mean, I could start with a DC supply at 0, but this is going to start with a DC supply switched on. If I had a capacitor, with a lot of capacitors in, and I wanted to see what all the rise times were as things came up, then I could start the DC supply at 0. So, having put that in, you will see that in this box here, it's automatically generated a SPICE command. It's generated a command called tran, which is transient, and it's put the time to stop. So it's a transient analysis over 20 milliseconds. So I click OK. It's done the analysis. So if I now put a probe on here, there's my source. If I put a probe on here, ooh, I've not got much of an output. Because we've got a huge capacitor there. So if I go here, what I should have done was drawn a wire out here and put output tab output. Well, I can still do that. So if I take one of those and I go OP output, that then gives me a tag, and then I can wire to that. There. Come on. Let's just oh yes, I can show you that now. I've actually accidentally done it. If because I clicked drag, wherever I put that component, the wires go with it. If I select move, it disconnects it.
You want a second output, Ray?
I don't need a second output because I'm not connecting it to anywhere. But what I do need, that wire is bent, so let me just do that. So that's the remove tool. So let me generate another wire. And let me move that and add that. on the end there. So that's our output. Because I've changed things, I need to rerun the sim. But it's remembered the plot points. So if I now go back to that, I need to click the window and that's not very good at all, is it? I've got DC on my output. So let's just change that to tile vertically. We'll delete that trace. We'll delete that trace. And we'll delete that trace. And we'll right click in the plot plane and we'll add one. And we'll add another one. So what's gone on? I add another one as well while we're at it. Let's have 4. I'll click in the top one and click that window and go on there. So there's my input signal. If I go on the other side of that capacitor, sorry, let me come back out of that. Let me get rid of that. Got rid of the wrong one. So we're in that plane. We'll put that up there. We'll click that pane and we'll go in there. So I've got a good signal here going into the base. But oh look, it's only sat on about 700 millivolts. That transistor is not on. So if I go into that one and probe on there, oh, okay, that's worked better than I expected. I was expecting that to be distorted, so I've obviously chosen the wrong value for that resistor network. I mean, they were completely off the top of my head. So, okay, what I expected to happen is, let me change that to, I don't know, 1K. Rerun the sim. That's what I expected to happen. Get a highly distorted waveform out, which is just sat on 6 volts. So that transistor is not conducting at all. And then the idea was to go in and change that. Let's make it, let's make that 2.2K now. Rerun the sim. And now we've got a much more representative amplifier. You've got the output sitting on a DC voltage, which is around about half the rail. So you've got the opportunity for the maximum voltage swing. Let's go into our source. Let's increase the output of that to 200 millivolts. Rerun the sim. So you can see now it's 200 millivolts peak to peak. My output, something quite right.
Yeah,
with
you've got
that.
200 millivolts coming out.
That's like misreading.
Oh, I know why. I haven't chosen a device for here. Aha. That's got minimal gain, that's why. So let's go in here. Let's choose a high gain transistor. Let's go for a BC847C. The C is the highest HFE, the B is medium, and the A is the lowest gain. So let's go for a high gain transistor. So if I zoom in on that now, you can see it's put a device in there rather than PNP. I know why it's low gain. Haha. Look at the amplitude there.
Yeah.
And look at the amplitude there. The impedance of that at 1K is too small. So let me make that a 10N. Rerun the sim. That's now giving me a much bigger output, but it's still not driving that into saturation. So let's change that to 100N. Rerun the sim. Now I've got distortion.
Like it.
So I'm now overdriving my amplifier. Now the reason I drew this circuit is because if I change my decoupling capacitor and put it here, and then change the ratios of these resistors, I can add some negative feedback to this. So let's just do that. Let's cut that, cut that, cut that. Rewire that to there. And let's make that 33 ohms. And let's make that 68 ohms, so we've still got roughly 100 ohms. Run the sim. And now you can see I've got less distortion, but we're no longer centered on sort of 3 volts-ish. I need to change these a little bit more, so let's make that 47 ohms. Make that one 47 ohms. Sim. We're now getting less distortion, but it's still too much gain. So I can either carry on adding negative feedback, because if you know, let's go into that pane and we put a probe on here, you can actually see the signal on the emitter. What I could also do is I could go in here, I could pick a new transistor, and I could pick one with a lower gain. Now we've got much less distortion. I'm still overdriving it. So go back to that and we'll make that say 150 millivolts. Every time you make a change, you have to rerun. And now we've got an amplifier that is giving us gain and not too much in the way of distortion.
Will you measure it for you?
If I could remember how. That I cannot remember, Bob.
Don't worry, just seems to do like American.
I mean, this is just a basic introduction. Really.
That's a good example.
So all of that we've done with no devices. You could now go and build that, and it would give you that performance. So that's transient analysis, but it doesn't tell us what it does in the frequency domain. This is just how it behaves, how it amplifies at a fixed frequency. So if I now go to, if I now go to simulate and edit simulation command, I now go to AC analysis, I can now sweep it over a range of frequencies. So we can have, this just determines the scale. So we can sweep it over an octave, over a decade, or we can do a linear sweep. Most audio stuff is either done over octave or a decade. So let's do it over decade. Number of points per decade. So this is the number of times it measures. So a decade is 10 hertz to 100 hertz, 100 hertz to a kilohertz, 1 kilohertz to 10 kilohertz, etc. So if we do, say, 101 points per decade, over 5 decades, that will give us 505 measurement points, which should give us a reasonable output. Start frequency, let's say we'll start at 10 hertz. Again, because it's units, you don't need to put hertz after it. Let's say stop frequency, 100 kilohertz. Okay, after it. So that, as I filled those boxes in, you'll see it's generated a SPICE command there. If I click that, I can add that to the schematic, and you'll see I already had a SPICE command in there, but those two commands are, they would clash. So it's automatically put a comment, semicolon, in front of that one. Okay, so now if I run the simulation, what that's given me is that. So that's given me a frequency response from 10 hertz up to 100 kilohertz. Now you'll see that the response is quite low down at 10 hertz. And the reason for that is simply that the input capacitor is too small in value. So you've got a high pass response between the two bias resistors and the input capacitor. And this trace here is also showing the phase shift which is caused by that RC network. If we go back to that, if I made that 10 microfarad, or I increased the value of those resistors by a factor of 10, for example, we'd still have enough to bias that transistor if I increased those resistors, but we'd then change the time constant on here, so that would give a much better low frequency response. So if I just do that, if I change that to 100K, change that to 22K, we run the sim. You can see now, instead of the rollover point being here, it's moved back. So I've changed it. No soldering involved.
Can you use it to sweep a component value as well then, so that you can look for an optimum?
Yes, you can. If I change that to C, C in a curly bracket. And why didn't that come out? So I've now taken that component. It's not curly bracket, is it? Let me do that again. Curly bracket, C, curly bracket. Okay. And then if I edit, let's use this editor. So I'm going to put SPICE command in now. So if I go dot step param and C, if I go 1000p, 10n, 100n, 1 mu, 10 mu. think that's all I need.
How have you attached it to that price?
Because I've now taken this value out, there's no defined value in there. The fact it's in curly brackets now relates it.
Right.
I know what I haven't put in here. I need to put list. With the step command, there's a number of different ways of doing it. You can either put discrete values in, or you can put a start and a stop value and a step figure. So if you're doing a resistor, for example, and you wanted to step it from 10k to 100k, you could put start 10k, stop 100k, step 10k, and it would go from 10 to 100k in 10k steps. I think I've got the syntax of that right. It will soon tell me if it's not. Sorry, there we go. There you can see all of the different values there. I put 5 values in, I've got 5 different graphs. So there's the different cut-off points on the different graphs. I could do a similar thing with the resistors and step the bias up and down, or change the load resistor, etc.
I guess that's a lot of the value with things, isn't it? Really, it's
Yeah.
just trying to find where the sweet spots are for things that are
Exactly.
otherwise longhand would be a pain in the proverbial.
Exactly. I'm aware that we lost sort of a quarter of an hour at the beginning, so I need to maybe move on from this one. So I mentioned PWM files, which not PWM, PWL files. Where did I put that? I thought it was in there. Okay, let's do an open. I think it's in here. Let's just do .asc. Yeah, here we go. Just take the grayscale source on its own. No, that one will do. That's that one. That one demonstrates. Why is that not coming? Not responding. Why are you not responding?
Because we're all watching.
That
is the usual reason.
Exactly that. Oh, I wonder if I chose a file that was on the wrong drive. Okay. Are you going to get out of this?
Turning it on and off again is good, but
Ooh.
bit dramatic. No, it's very clever.
Supposed to happen. No, you don't want to report it to Microsoft.
I wonder what they do with all those reports. Ignore them.
Yeah, patently.
People beavering away, worrying what's going on.
It's probably worse than that. They probably use them to work out how they can really annoy you with their
Yeah. Well, exactly. Yeah. Make that picture.
Yeah, here we've got a
This is work.
Here's
Well,
what's all the
okay.
things that really annoy our customers.
Just block it from downloading that one in the future, so you can't do it again.
Yeah. The main thing is starting is changing the start menus. Let's do that big time.
Yeah, keeps them quiet. Ray, I know this is a silly question. What is that background? Is it a watch? Or
Yeah, it's a watch.
I think that's the Antikythera mechanism, that ancient Greek mechanism.
Greek mechanism.
Yeah, the Antikythera, I think it's called.
Yeah.
Something like that. It was supposed to be 3,000 or 4,000 years old.
Was it the
Navigation thing, was it?
analog
I
computer?
think it's a star predictor or a
Yeah.
navigational aid,
Navigation, like a sextant type thing, yeah.
which is far in advance of things that were, you know, a few hundred years old.
Aliens.
Aliens, yeah.
Aliens, yeah. The Greeks.
Either that, or it is just a coffee stain.
It's
Which
traditional.
we're now spending years trying to interpret.
Yes.
Some academics have got a whole career out of
Thesis
that.
of it.
That's how BBC Television Centre ends up round like a donut. That's where the architect with his coffee.
And Milton Keynes.
Yes.
That's what I used to like about Time Team, wasn't it? They'd find a fragment of a leather boot or something like that, and then from that they would extrapolate the whole village and several of the people who lived there.
All lived with the same foot.
Yeah. Here's Barry, he lived in what's gone there. Still, you've got to spin it out for an hour, else you
We
can
got a
go.
manic presentation of Tony Robbins.
Well, you've got to have that.
Yeah.
Yeah, it should be okay. I don't know why that didn't open.
I've got to admit, although I'm a bit of a skeptic, Ray, I do use these things for the switch mode housefly stuff. And there's some very good free developing software packages for that, for different manufacturers.
Oh, he does not like.
So you buy your cheapest components, shove it all in there, see what works best with those.
No, when you're trying to choose a buck boost converter or something like that, you know, it's quite a mission. And as you say, a lot of the manufacturers do some very good. You type in voltage, type in current inputs, and suggest a few, and then pop them in a circuit.
He doesn't like that file for some reason. I had it working
Then
earlier.
you find you can't buy it yet, because that's another story.
Yeah.
Okay, we'll skip that one for the moment, but you can you can actually enter a file which defines a waveform. There's one more I'll try, and if it doesn't work with this one, then
Is the file just,
it's just a numeric. It's just a text file that gives you max and minimum values and a time step.
right, so it's just a sample?
So if you wanted to generate a staircase waveform, you would generate a time step, an amplitude, a time step, an amplitude, a time step, an amplitude. And then when you incorporate it, you could put repeat. So it would generate.
Effectively, you tell it where the coordinates
You tell it what the coordinates are. Yep.
Yeah.
I don't know if I can find it.
Definitely advantage.
Let me just want one more go.
Otherwise you want the transistor on a bit variable.
Which one's quicker?
It's quick.
You it's the print on to do.
Probably helps our Chinese cousins work out which components they can drop out when they ship them over here.
Well, you can start the EMC stuff first.
They can do all that work without actually having to build them and waste time.
Field sync. Let's.
I'm actually going to look that one up now. I've read it's a grand deck actually. I read it.
No, it's not going to do it. I don't know why that's suddenly stopped.
Has it, when it crashed before, has it got a process running that it hasn't terminated and now it's fighting with it?
That's possible. Might have to do a complete reboot, but
We'll just go to Control Shift Escape, and it should bring up Task Manager. You might be able to see if there's a process running that you can just end.
No, that's what I did.
If you did that, maybe it was.
But it comes up on my screen here. So Chrome.
There is a spice not responding, but
Yeah.
maybe if you squash that, then it'll free itself
Go
up.
back to where it was before.
End task. Okay. More time. If it doesn't work this time, we'll move on. No, that should have come up. It should have come up instantly. Oh, it's crashed.
Well, don't worry, Ray, it's a very good
Yeah,
tool.
It's crashed.
Because if you go too much further, my brain's going to fall.
We do believe that it works, honestly.
That's what confused
It
it.
does not like it.
That was the only time I'd ever seen it used properly, so thank you for that.
Let me just
To what
get.
extent does the SPICE library actually model complex integrated circuits that are actually available?
Sorry?
Does the SPICE library actually model? I mean, I can say it's very simple, using a simple transistor like that. It's very straightforward, but most of the time you're talking about building something around a complex chip.
Oh yeah. There's complex chips in the library.
Yeah, so you can get those with all the characteristics built into them.
Where's the? I can't see him not responding there.
Is it the streaming thing? Because Google was running red hot
Close
there,
it,
wasn't it?
Chrome.
Chrome.
Yeah.
That's going to be that works because you're streaming or something.
Well, that's the Jitsi, isn't it?
Yeah.
So I can't close that.
Um,
Okay. We'll bypass that one then. Now, this is Bob's fault.
My favourite subject.
Your favourite subject. I actually added quite a lot more to this talk because conversation we had yesterday.
Because of, oh, I'm sorry, Ray.
Well, you had a good point. I mean, having extolled the virtues of Spice, LTspice is, and in particular, there's one component that's impossible to simulate accurately, and that's a transformer. Providing a transformer is operating in its linear region, there's no real issues.
Transformers aren't too bad, but audio transformers. This came from a BBC thing I had years ago when we were doing lots of mono to stereo stuff. And I was telling Ray about it yesterday. One of the very professional audio companies came along and said, "Oh, we designed you some mono to stereo boards." "Oh, no problem at all." "Wacko, where's the prototype?" "Oh no, you're prototyping. We do it on computer model it." Okie dokie. Because what I got back was absolute rubbish.
I mean, to do it properly, you need software that's designed for non-linear simulation, which is not what Spice is about.
Also, to be fair to the audio transformers, right? Just doing the audio transformer is definitely a black art. There are
Yes.
very few people, Mr. Souter and people like that, would go into the cabin at the bottom of the garden and mix IF Toad and they go back.
We need to get through this fairly quickly because there's quite a few slides on this.
Yeah, okay, cool.
There's no circuit symbol in Spice for transformers because no two transformers are the same. You can have multiple windings with core, without core. But we can make one by taking 2 or more inductors and coupling them with a SPICE command called a case statement. So we draft an inductor for each transformer winding and we couple them using that directive. And we can have 1, 10, 100 transformers, as long as they've got different numbers. So K1 is for transformer 1, K2, K3, etc. And you can have any number of inductors, L1, L2, L3, which all represents the windings. And the last number 1 at the end is the coupling factor. So obviously when you wind a transformer, you've got normally the coupling really tight because one winding's over the top of the other and you've got a core around it. There would be an exception for some things like a Tesla coil, where you've got a small coil at the bottom and the rest of it is not coupled very closely. You might only have 10% coupling, so in which case that 1 would be a 0.1. So it can obviously be range between 0% and 100%. And obviously it's 0%, you haven't got a transformer, so a bit silly, but you can actually go over that range. So there's a transformer representation in SPICE. So L1 is obviously the primary, L2 and L3 are secondaries. The statement that we had above, which is that one there, K, L1, L2, L3, and a coupling factor of 1, couples those all together without them actually being coupled in the diagram as such. You don't have to draw a core or anything in between them. So that is equivalent to that. If you had one of these windings, which, if you remember back in the old days of TV EHT transformers, you had all the windings on one limb and the EHT overwind on a separate limb of the transformer, because it was a ferrite ring, a square ring, but so there was less coupling on one of the windings. So you could have that statement and have one of these that had 0.5, for example, so it was less coupled to the others. So you can actually vary it. In that case, you would need the 3 different statements to state the coupling between the different windings. So the next issue is, how do we define turns ratio? So it's done by specifying component values, not individual ratios, not turns ratio directly. It's individual component ratios. So the inductance ratio follows that formula: L primary over L secondary equals N primary over N secondary. So it's N turns to 1 squared. It's the usual transformer equation. So if you've got a 3-to-1 transformer, then the impedance ratio is 9-to-1. So the value of your inductors needs to be 9-to-1 for a 3-to-1 transformer. For a 2-to-1 transformer, they need to be 4-to-1. So that's what we've got there. The ratio between L1 and L3 is 9-to-1, so that's a 3-to-1 transformation. It's a 9-to-1 impedance change, and this one is a 2-to-1 transformation, a 4-to-1 impedance transformation, so it's N squared to 1. I was going to return to LTspice and try and simulate that, but considering it's crashed, I don't think we've got time to waste on doing that at the moment. So we'll take that as read that it simulates. That was an ideal transformer. No transformer on this planet is ideal. They're full of parasitics. For a start, you've got interwinding capacitance. You've got winding wire resistance. You've got capacitance between turns, and you've got leakage flux or leakage inductance. So what does all that mean? It means that you've got losses, you've got unwanted coupling, you've got all sorts of things that you didn't expect. So our ideal transformer has no leakage flux, no leakage inductance at all. But we know in a real transformer, nothing's perfect. Transformers is another lecture in its entirety. But leakage inductance is that all of the coupling between the 2 windings isn't 100%. And if we wanted to measure that, we would measure the inductance of the primary whilst the secondary was shorted, and you would get a much lower value than the normal primary inductance. So that would then give you the amount by which it's not coupling. Non-linear transformers. I mean, we've seen we can reasonably easily model transformers in their linear region from those last two slides. Even the one with all the parasitics on, you can model reasonably well. But if you've got something like a power transformer with a core that will saturate at a certain magnetic flux, then the characteristics of that transformer change at that point. And if you can remember your magnetics, this is what's known as a BH curve. It's the magnetizing current versus the magnetic field. So when you first switch on, it starts at 0. Your current rises to a point where saturation starts. If this is an AC transformer, then the current reduces, but the magnetism doesn't go back to 0. There's a certain coercivity. And the same happens when you go through. So you end up with the magnetic field going through this hysteresis loop, as it's known. And the fatter that loop, the bigger the losses in the transformer. If you extend that by increasing the voltage across the primary or increasing the magnetizing current, there comes a point where the core will saturate. And at that point, it's no longer linear. You're no longer getting an increasing current for an increasing voltage across the winding. At that point, things go rather south. So that's our normal simulation for an ideal transformer. So you've got, you can just about see you've got a green trace there, which is the primary, and the blue trace, I think, which is the secondary. So nice sine waves, no distortion. So you've got a good input and output waveform. If we overdrive that transformer so that the core goes into saturation, as soon as the core saturates, the inductance of the winding reduces. So you've no longer got a back EMF effect opposing the applied voltage. So the inductance drops and the current goes up. Normally, in its linear region, the current would be going up and down sinusoidally around here. But as soon as you reach saturation, the current shoots up. As soon as you come back below saturation, the current falls back to its normal level. This circuit here, which is using voltage-controlled current sources and inductors and all sorts of things, is an approximation of a non-linear transformer. I only really found this yesterday, because I was looking for something that did non-linear transformers, and someone's written this article, but I've not had a chance to put it together or simulate it. But it allegedly gives you that, which is what you'd expect from a saturated transformer. There's lots of material on transformers. There's 3 YouTube videos I found which are quite informative. This one just talks about understanding transformers. This one is about developing a simulation model, so it's actually measuring the parameters of a real transformer and then trying to put them into a SPICE model. And then further down, it's trying to improve the transformer model with bench testing. 3 quite interesting videos. And then there's quite a bit of stuff on the analog website itself. There's 4 or 5 different links, 6 different links there, which if we had more time, we could look at. But I'll put those up on the .io website, and we can have a look at those. I think this last one, I don't know if I can link to that. Open hyperlink.
Is the coupling factor K on there? Is that purely linked? Is that purely designed with respect to inductances, or could it be used for any mechanism of coupling between two points?
Well, the coupling factor is basically telling you the goodness of the coupling between the transformers, between the windings. It's an expression of mutual coupling.
Which means it could be a transmission link for anything you like.
Yeah, it could be. I mean, it could be an ATU. You could have an air wound coil,
Yeah.
in which case you don't have to worry about non-linearity. I don't know if I can get this one up there. This is the article, how to use non-linear models in LTspice to simulate characteristics of transformers. So, you know, it's quite, you can see where I pinched that from. You know, no plagiarism here. Oh, I pinched that one as well. So this is his schematic there. So that, you know, there's a fair amount of, oh look, we've seen that one before as well. But yeah, there is quite a number of useful articles on the web that I found. Let's have a look at that one. So there's this series of videos. There's the getting started, which is more or less what we've done. There's essential LTspice topics, creating third-party models, behavioural sources. So if you want any more information, just go to the LTspice website. So you can see what we've covered: transformers, defining stepping variables, piecewise linear sources, which is the one that wouldn't work. There's voltage control switches. There's a whole load of stuff just purely dedicated to this. Third-party models, how you import third-party models, how you create and edit schematic symbols, how you manage the libraries, etc., etc. So all of it's there. You don't have to register on the site. You just go straight there, and it's there. There's no people plaguing you with emails. It's completely free to use with no hassle, basically.
It sounds ideal, right? Thank you for all this. Very much appreciated.
Sounds like some of the talk in it as well.
Yeah.
Yeah. Oh, it's a huge subject.
Yeah.
I mean, I've probably used about 10% of what it would do in my career, and I've used it a lot. I've used it a lot. I don't know if I can quickly find it.
Have you ever
It probably won't come up because it's crashed.
done a simulation where you just click the little running man, then go away for lunch and come back again before it finishes?
In the early days, when you had computers that had very little memory and were constantly Windows page swapping, and but not recently, no. I think the biggest circuit I've simulated, I don't know if you remember back in the 80s, there was a guy called John Lindsley Hood who did a really high quality audio power amplifier. I've actually created that in LTspice and simulated it. That's probably the biggest one I've done.
I used to use a package called Proteus.
Yes, yeah.
Proteus was interesting, but the emphasis really was on translating the circuit into PCB manufacturing, which was not really what was interesting.
No, but a lot of things like I mentioned Altium, because I worked with Altium when I was at EDMI. They have got SPICE simulators built in, and the one Bob did his talk on has got a simulator built in, but they are limited. I mean, even this is limited, but it's probably one of the better ones because it's been written specifically for complicated circuits and to run fast while it's doing it.
Yeah.
Okay, well, I
That's
think
great.
at that point, we'll call it a day.
Put some lights on. Yeah, no lights outside. Is that right? We're on time.
Ray?
Yeah.
What's the earliest year that you used it?
I've been using it probably since 2012, 10 years at least.
Okay, I was interested in what the original interface would have looked like.
I honestly don't know. I mean, I worked for Wood and Douglas for 28 years, from 1989 to 2017, when they made us all redundant after they got taken over. But I've used analog devices and linear technology chips throughout all of that period. And it was only around, I'd say 2010 is probably the earliest that we came across at 2010, 2012. And it came about because we had an engineers seminar at our building with Arrow, which is one of the broadline distributors that we were buying components from, and they happened to bring in Simon Bramble and Hanif Rashid from LT, as it was then, bringing their wares, and they happened to mention. Sorry.
It had a Windows interface, basically.
Oh yeah. But Hanif and Simon said, "Oh, we're doing a seminar in, I think it was Newbury at the time. You should come along and have a look at our new simulator." And I sort of went to. They had seminars about every 2 years, and obviously you could see it growing and expanding over that period of time. I went to about 5 over a period of about 10 years. But I think Mike Engelhardt is now. He must be in his 70s, so he's probably not doing the globe trotting anymore, especially with COVID. But I noticed Arrow are doing some online seminars. So if you want to look at the seminars, do go to Arrow or do LTspice Seminar 2022, and that should take you to. You'd have to register with Arrow, but